Okay, so I am Ben Walker, tech lead for SPDK, and I will be presenting along with Seth Howell, who's one of our other software engineers. Many people in the community know Seth from doing all the CI stuff. A lot of people interact with him frequently. We're going to be talking a little bit about what we've done in the last year for NVMe over TCP, for leveraging some of the new features that the kernel has added around TCP sockets. And so the agenda is going to go like this. The first two sections are going to be covered by Seth, and he'll talk about NVMe over TCP design considerations, some background information, things we talked about. Then he'll go into some of the things we've done recently, our current techniques, what the software does today, and why that's effective and good. And then he's going to hand it back over to me, and I'm going to talk about some more future-looking things, things we'll do in the next year or so, around first IOU ring, and then some even Praiser ideas, to put it one way. So with that, I will hand it over to Seth.
Great. Thanks, Ben. Appreciate that. So something Ben didn't mention is I've had the great opportunity to sit next to him in a lab for the last few years, and I got a lot of firsthand experience, watching him and ZA work through and think through a lot of these design considerations and performance enhancements. And I can tell you there was a lot of thought and a lot of work that went into this. So I'm excited to start going through some of these. Next slide, Ben. Great. And next. Perfect. So when you think about SPDK, hopefully the first thing that comes to your mind is performance. And this is true for every module that gets developed inside of SPDK, especially for NVMe over fabrics. We already had a pretty good foundation of performance when we started working on the NVMe over fabrics TCP target. We had the RDMA target already in place and a very good generic framework in both the initiator and target side for plugging in the TCP module. But of course, with network stacks, your performance is not just in the IO path, right? It is in the IO path, but it's also in the number of connections that you can handle concurrently. So with adding the TCP transport, this is definitely something that we had to think about. And so for those of you familiar with the C10K problem, it's the idea of being able to scale your number of connections to a very large amount without suffering a performance penalty just for having connections open. Next. Great. So there's a few, ideas and ways of managing this out there. The most naive way of managing your connections is having a single thread per connection and using blocking IO. And this, obviously for SPDK was not an option for us. As you start adding more connections, it's going to fall over very quickly. And using blocking IO in the first place just doesn't fit well with the SPDK model, right? Where we're all asynchronous and polling. So we immediately jumped to the second strategy of having many connections on a single thread, and then using edge or level trigger notifications. So on your Linux side, that's going to be epoll, or there's the BSD equivalent of KQ. For those of you familiar with that, we're currently using this in the TCP module, and it's working pretty well for us. But we definitely believe that there's room for improvement. And the ideal for any SPDK application is completely asynchronous I/O. Currently, we don't believe there's there's sufficient OS support to do a completely asynchronous I/O in TCP, but we think it's coming, and that's something that Ben is going to touch on more in his slides going forward. Great. So, you know, the TCP transport was a long time coming, and I think a lot of people were very excited about it. You know, there's some basic inherent pros to using TCP. You don't need any new special hardware. A lot of people have it, you know, already in place. They've been running TCP for decades. You know, their hardware and networking is all based around it. It's going to run on any operating system out of the box. And it's a programming model that we're all used to. But with these pros, you're going to run into you know, cons. Some of them arising specifically from the pros, right? You don't have special hardware for your, you know, for your networking, but that means that, you know, relative to RDMA, you're going to have heavier CPU usage because you're not offloading some of that work to the NIC itself. You have direct, you know, operating support for your TCP stack, but that means that that's going to be running in the kernel, and your application is going to be running in user space, so you've got data copies going back and forth. And finally, there's going to be a much heavier system call overhead as opposed to RDMA. So our big question that we asked ourselves is, what can we do in SPDK to remove these data copies between the kernel and user space and reduce the system call overhead? And so we'll be going through, you know, everything that we talk about in our current techniques and future techniques is really going to be centered around those main ideas. And can you hit next one more? Great, thanks, Ben. So just a quick reminder about some of the architecture of the NVMe-over-Fabrics target. The traditional structure is, if you look all the way on the left there, for every CPU core, we're going to have a single SPDK thread on top of that. And then we're going to group connections based on a poll group. For each transport, what that poll group corresponds to is going to be different. For those of you familiar with RDMA, that's going to be something like a shared receive queue, a shared completion queue. For TCP, it turns out that's going to be a group of POSIX sockets. And recently, we, in addition to having that generally available on the target, we've also added poll group support on the initiator. Next. So this poll group abstraction that exists on both the target and initiator made it very simple for us to group, it gave us a ready abstraction over which we could group our connections per thread and poll them using ePoll. Next. And so ePoll is a fantastic tool when you don't have 100% of your connections busy all the time, because it allows you to get a callback and only call receive on the sockets that specifically indicate that they're ready to accept more data. Of course, this can be seen as a trade-off. In the event that every single time you call ePoll, every single connection has data available, you're going to introduce a little bit of extra overhead, but generally speaking, not all of your connections are going to be busy 100% of the time. So we see this, this connection grouping as a huge plus, and we enable it by default. So another another optimization that we have on the receive path is in how we actually bring the data off of the socket and into data structures. So when you're receiving data off of in NVMe over Fabrics, you're going to have two types of data. The first one is going to be your data buffers, and the second one that you're going to bring in is going to be either your command or your request structure, right? Your buffers are going to be, 4K or larger, but these command structures and completion structures are going to be quite a bit smaller, 72 bytes and 24 bytes respectively. So what was being done, in the original implementation of the TCP module is we were receiving each piece of data using a separate syscall. So that meant if we were getting, if we had a whole string of completions, each one of those was getting received directly into a data structure using its own receive call, which, as you can imagine, on a workload where, say you're on the initiator side and you're only doing writes, you're just going to be getting back completions. And that's going to result in a lot of time switching back and forth between the kernel and user space. So in some of our traces, we saw up to 50% of the time being used in that transition. So that led us to, to say, okay, this is an obvious bottleneck. This is the top thing that can change. And Ben had just a really great, in my opinion, it's a really simple, really elegant solution. And he introduced to SPDK this pipe structure, which is essentially just a circular buffer that has two pointers, one of them for reading and one of them for writing. And the API for this pipe structure is very simple. I think there's 5 or 6 functions total. So you start out by creating a pipe, and it initializes a read pointer and a write pointer at the beginning of this buffer. And then when you're ready to write something into this pipe, you simply request a pointer into that pipe with SPDK pipe write get buffer. And then once you've written into the portion of that buffer that you've retrieved, you simply call advance with the last bit that you've actually written to, and it advances that pointer. After that, you can read all of the data up to that write pointer with 2 symmetrical calls with the reader pointer. At that point, you're free to advance the writer again up to the point where your read pointer has been advanced. So you can actually, at that point, begin looping back over the structure. So, like I said, it's a very simple structure that Ben introduced and immediately put to use in the receive path for NVMe over Fabrics TCP. So what ended up happening is in our socket abstraction layer, we create a pipe that's approximately 8K, slightly larger actually. The total size of this pipe is 2 encapsulated data worth of I/O, and so that's going to be the 4K buffers plus 2 commands, slightly larger than 8K. But we immediately copy that from the socket to the pipe, and then as the NVMe over Fabrics TCP module requires that information, it parses it out of the pipe and copies it into the corresponding either data structures or buffers. So this is a trade-off. Again, we're adding an additional data copy. We're essentially double buffering through that pipe, but we're drastically reducing the number of system calls. And for any real-life workload, right, where you've got mixed reads and writes, you're going to have a lot of these smaller command structures that would be very small copies, that you're incurring a system call for each one. And that's really where we see the performance benefit coming in on this. So as I mentioned, for these small command structures, trading this data copy for fewer system calls is way more efficient. And for those of you that were wondering what is the purpose of the 8K size on the receive buffer or on the pipe, it's because once you get past a certain size for this buffer, it doesn't actually become any more advantageous to copy. The cost of copying is going to scale linearly, while your system call just has a consistent cost to it. So we cap the pipe size at 8K so that we don't overextend ourselves there, and it keeps that trade-off in the positive. So that was over on the receive side. Now we're going to move to the send side of the connection. And again, send message, we're going to be incurring a lot of system call overhead. So luckily in SPDK, we're polling, which means that we have a regular cancellation point where you can accrue work in between polling calls and then submit it all at once. So in both the target and the initiator, we essentially have a function where we check for completions, and that is our cancellation point for polling. Okay. And essentially what we do is we queue everything up on, we're going to queue everything up, all the send message calls, and then as soon as we're done processing completions, we submit all of those as a single send message. And this has been a huge performance benefit for us. We have seen, sorry, I'm advancing my slides as well, but in practice, this is a 30% or more performance improvement, and it can't possibly hurt you. Worst case scenario, you're going to get a single send message call in the queue, and that's going to turn out to be exactly the same number of syscalls you would have done in the past. It's hard in an actual workload to predict exactly how many send message calls you're going to get in between each poll. But you can just think about that math is the cost of a single syscall is going to be constant, and for any number of IL that you batch together, it's going to be that many times a performance benefit. Okay, next slide. So something else we've been that was worked on on the send side is this newly added message zero copy socket flag. This was added in Linux 4.14, so I guess it's not entirely new now, but it was something that came out around the same time, and we put it to use. So what message zero copy does is it actually allows you to pin your user space buffer, and then instead of copying that data out of that buffer to the socket, it's going to send that directly through. The problem with this, of course, is that pinning is not going to be free. And you have to have an extra syscall because you get notified of the completions on the error queue. So there's some public guidance on this, and there's also a lot of experiments that Ben has done. The public guidance is that message zero copy is going to become effective when you're sending about 10K of data. With the experience that Ben has done, we found that at about 4K, we have a wash. So that removing that extra copy But taking the time to pin the memory is about the same. But when you get to 8K, where you're already seeing a huge benefit. So we always have message zero copy enabled on the send path. So that is a summary of kind of where we're at right now. At this point, I'm going to turn it over to Ben to talk about IOU ring and then some of the other more future-looking portions.
Cool. Thanks a lot, Seth. Yeah, so now we're going to turn our focus a bit to IOU ring. And as I cover this, I want everybody to think of this not as me being the definitive source of how IOU ring works, but rather our experience so far in using IOU ring. And I just want to be very upfront that this is still very much a work in progress. There are a lot of open questions. We do not know how everything works just yet. Not everything is hooked up in the kernel. So this is a sort of an active area of development going forward, and things may change. So let's start with what is IOU ring. So it's a new Linux I/O interface for interacting with basically any file descriptor. And it was originally designed as a new libAIO to do async I/O for storage. And it was cool. The initial patch to the kernel included comparisons to SPDK. So we know at least what part of the motivator was. I've heard also that RDMA is a major motivator for this, or inspiration for it, as is NVMe. And so obviously SPDK is modeled on NVMe as well. While this was started as a mechanism to do async I/O to storage, what it has really become is a mechanism for making any Linux syscall asynchronously, and which is a really interesting concept. So again, this thing is not entirely baked. It changes all the time. We just got Linux 5.7 maybe 2 weeks ago, and it had a bunch of new stuff in it, and it changed everything. And so this talk is, kind of the current state of the world. We're probably even slightly behind in our understanding because, they released something 2 weeks ago. We're trying to keep up and then push them in the right direction as much as possible, but everything could change next Linux release. And so just some, my editorial comment. Well, I think this is really cool for storage, and SPDK has a BDEV module that uses this for storage if you want to use it to talk to a SATA device or a SCSI device using the kernel drivers. That works really well. Actually, we see quite a bit of performance improvement there. It's not nearly as fast as using SPDK directly to an NVMe device, but it is significantly faster than previous possible interfaces. And last year at SNIA SDC, John did a presentation of some performance benchmarking of IOU ring as it was at the time. And he shows just how much better it really is than previous Linux interfaces. It's like an order of magnitude better almost. And he even has some comparisons to SPDK, which it's like another order of magnitude faster to use SPDK. So how does an IOU ring work? So the application creates a U-ring, which stands for user space ring. And there have been some complaints about the term U-ring. Just make sure you get that G in there. Don't let that letter change. But it is a user space ring that consists of a submission queue and a completion queue. And so anybody who's familiar with NVMe might see some similarities here. The entries in the submission queue and the completion queue are fixed size descriptors. A user then can, an application can then create a ring. The rings are not thread safe, so applications either need to take a lock or just create multiple rings, one for each thread. The application then can drop descriptors into the ring. The rings live in application memory, so this is not a syscall. And the descriptors have a file descriptor and an opcode, and the opcodes are syscalls that you would be familiar with on Linux. And once you've dropped all of your descriptors in, you can make a real syscall, a new one called IOU ring enter, to sort of ring the doorbell, to use an NVMe term. And this tells the kernel, hey, I want you to go do all these things that are described in the ring that I just gave to you. And the kernel says, okay, I'll go do them. And when the kernel's done with them, it places completions into what I have here is the orange, the darker orange boxes on the right, which is the completion queue. And it drops completion descriptors in that said, okay, I completed this descriptor you gave me with this status code. And they don't necessarily come in order. It's just like NVMe. It just completes them as it finishes them. So with that, IOU ring actually has a couple of different modes that it operates in. One is what I'll call the default mode, pass no flags when you create the U-ring. And that means when you submit a command or a descriptor into the ring, the kernel will go off and it will try to process it. And then it will submit maybe an async operation to the underlying hardware if that's what's going on there. And when that operation is done, the device, the underlying hardware, will generate an interrupt. And in that interrupt handler, or in a deferred handler after that, it will eventually place the completion queue entry, completion queue descriptor, into your application's completion queue, which you can then pull and find. And so this is sort of still an interrupt-driven mode. The device is async with interrupts. But then there's two more modes that you can select when you create the ring. One is called IO poll, and it's an application-driven polling mode. And this is basically, quote-unquote SPDK mode. So what actually happens now is when you submit the command into the ring, the kernel will take that within the syscall to ring the doorbell. It will grab the descriptor, figure out what you want to do, submit if it's an NVMe device under there, it will submit an NVMe request, NVMe command to the NVMe submission queue. That submission queue will have interrupts disabled. And so it will send it to the device and return. And then nothing will happen unless the application polls by making more IOU ring enter syscalls. And so in the syscall, it checks for new things submitted, and it checks the underlying hardware for completions. And then it will post completions back to your completion queue if it finds them. But this is sort of, nothing happens in the kernel. It's completely passive unless you poll it. This is only supported on, currently today, file descriptors that are open in ODirect mode, which means it doesn't work on sockets and files and things like that. So this is really most useful for talking to, today, NVMe devices through the kernel. And in fact, when we open a block device and use this in our BDEV module, we use this mode. Then there's a third mode called SQPoll. I think stands for submission queue poll. And what this does is it spins up a kernel thread. And what the kernel thread does is it polls your submission queue, waiting for your application to submit descriptors. And when it finds them, it goes off and submits them to the underlying hardware, waits for it pulls that device for a completion, and when it finds it, posts back the completion to the completion queue. And so in this mode, we don't actually ever have to make a syscall from the application. We don't have to ring the doorbell to tell the kernel to go. The kernel is polling us, us as the application. So the main advantage here is there's zero syscalls in this. We've done all of the operations we want to do with no syscalls at all. The disadvantage, of course, is that we've spun up a second thread in the kernel. There are mechanisms for the kernel to go to sleep on that thread if it passes an idle threshold, and it'll write a bit into the ring and say, I stopped polling you. And when the application goes to submit new descriptors, it can just check that bit and say, oh, if the kernel went to sleep, I can make that IOU ring enter syscall and spin the thread back up till I'm going to be busy again for a minute. So we actually think that SQPOL mode is probably going to be the best mode for networking because it has the most syscalls, and it's probably worthwhile to avoid them all and burn the extra thread polling while we're busy. Okay, so the next section here of IOU-ring, the way this is going to go is IOU-ring added basically an async send and an async receive. And we want to try to use this on sockets. And so I'm going to have a little conversation with myself in the form of question and answer, where like past me, when we first sat down and looked at this, is going to ask a question, and current me is going to try to answer it. My answers are not always going to be sufficient, but I'm going to do my best. So, you know, when we first started thinking about using an asynchronous send on a socket, one of the first questions I ask is, well, would we still mark the socket as non-blocking with this? What does non-blocking mean if the whole operation is async by, you know, the fundamental API design? And I don't really have a good answer to this one still, except that in real tests, setting the socket to non-block does seem to improve performance. And so what I suspect is that in low memory conditions in the kernel, where it's struggling to find resources to queue up your requests, like it's run out of buffer space or it's run out of request objects or something, I suspect the sort of ring the doorbell call blocks. But if you make it non-block, what it'll do instead is I think it will make it so that it does a partial send. It just sends what it can, and then or it fails your request and says I didn't send anything. And it's usually better to back pressure us by, you know, the application by not sending everything we ask for than it is to instead block. That's what I think, but I don't know that for sure. So this is related. If you have an async send API, do you ever get a partial send? You know, my gut reaction was probably not, right? Because it would just wait until it could send it before it told me it was done. But the answer here is definitely yes, you do get partial sends. And I think this is related in most cases to having non-block set. But if the kernel doesn't have the resources to be able to queue up your request, then it will, you know, either not send, it'll tell you it's sent 0 bytes, or it will partial send if it has some requests but not enough. We're not sure of all of the possible conditions here. We currently think, even if we remove the non-block flag, that there would still be conditions where it could partial send, possibly. So we write all of our code assuming they're possible and can be handled until we understand this better. Okay, and then another question was, you know, Seth outlined this whole strategy for write batching that we currently employ to gather up all of the different writes we want to do on a socket into a single large vectored write. And that's given us a lot of performance improvements. If we can just submit multiple requests all into the ring and then ring the doorbell once, so a single syscall, is this still important? Do we need to do this? And so what's clear now is write batching is no longer necessary to reduce syscalls. It might still be slightly more efficient just to traverse the kernel stack fewer times, but certainly the batching effect to minimize syscalls is no longer necessary. Now, note here, I didn't answer the question yes or no. I just said for the reason of reducing syscalls, it's not important. So we'll do some more questions here. This is a tough one. If I were to submit 2 asynchronous writes, you know, sends on the socket, and I hit one of these conditions on the first one where the first is only partially sent, what happens to the second one if it's already submitted? You know, this is a TCP socket. It's a stream of data. Things have to stay in order. And the reality is that second one really could send anyway. So imagine, you know, I submit a send with some data, 4K of data, let's say, and then some other commands, some like receives or something on the, you know, or descriptors for other sockets. And then another send of 4K. And the first send tries to send and says, I can't. maybe I could send 1K, but then I'm out of resources and I can't do any more. So it does a 1K, it sends 1K of your 4K. And then it processes more stuff, and an interrupt comes in and interrupts your thread, and it processes some things. It frees up some resources. And then your kernel thread keeps going, and it tries to submit the next send and of 4K, and it says, oh, I have resources, and it sends it. Well, we just left a 3K hole in the TCP stream. And so we can't do that. And so what we do today to fix this, and there's a lot of ideas around how to do this and alternatives that we'll discuss, but what we do right now in the implementation is we enforce a single send message per socket at any time. So it's always queued up 1. And of course, to make this efficient, we put back in send message batching. So for every poll loop, we gather all the send messages that the user wanted to do, and we submit a single large vectored send message asynchronously now to the socket and say, can you send all this thing? And it may partial send and it may not. And then sends that come in while that one's working are just gathered for the next cycle. So this works pretty well. This asynchronous send, I should mention, is sort of like the send syscall, where it's not waiting to complete on the sort of acknowledgement that data actually arrived at the other side. It's waiting only, it completes the asynchronous send once the data has been sent on the wire. And so in the default mode, it's just got to buffer it into the kernel TCP send buffer in order for it to successfully complete the whole thing. And so these async send operations are not usually outstanding for very long. There are alternative ideas here. There's a feature called IO link, is what I'll call it, where you can submit multiple descriptors into the ring at the same time that are linked together, but they have to be submitted sequentially, so there's some challenges there. This may ultimately become part of a better solution. All right, and so now let's switch over and ask a bunch of questions about the receive side. The first thing that this is good for, and one of the best things it's for, is replacing ePoll. And so there are async poll operations, interestingly enough, in IOU ring. You can submit a poll-in operation asynchronously, and it will complete when there is data that can be received on the socket. And so one way to replace ePoll use is to submit a poll-in asynchronously for each socket, and then just check for completions on the ring. When they complete, you can make a receive message call, and everything is done. This is fantastic. And you can then basically check the ePoll, check the poll operation without making a syscall because of the way IOU ring works. But alternatively, could we just submit an async receive message to each socket and not poll at all, and just wait for the async receives to complete? Well, the answer is that didn't really work so well because of the way the kernel was plumbed prior to Linux 5.7. But as of Linux 5.7, there is a feature flag, and it's IO feature fast poll is supported. Yeah, you can just do this, and it works efficiently throughout the kernel. So you don't have to have any polling at all. You just submit a receive asynchronously for every socket in your group, and when it finishes, you get your data back. And so some of the other benefits that are semi-related, checking for the completed descriptors does not require a syscall because it's dropping completions directly into your completion ring. Poll-in operations can be batched with sends, so the syscall overhead of ePoll, even when everything is entirely busy, is eliminated. There's no overhead of that. Further, each descriptor in the ring can point to a different file descriptor. So you can actually batch across connections. So all sends across all connections in the poll group can be one syscall, and all receives and all polls. So you effectively end up doing one syscall per poll loop per poll group, and that's it. Okay, so I'm just going to wrap up here with 2 slides on future improvements, and these are like half-baked ideas, things we're looking at that I just want to mention that are coming our way. In the strategy where we do an asynchronous receive message for every single socket, that means we have to provide a data buffer up front. And so since we do this 8K polling strategy, we have to allocate an 8K buffer for every single socket. And if we have thousands of them, that takes too much memory. But fortunately, the kernel guys thought of this, and in Linux 5.7, just a couple weeks ago, added a new descriptor type called IO-ring provide buffers. And this lets us submit a descriptor to the pool, or to the ring that contains a data buffer, and we can submit a bunch of these. And what we're doing is we're basically giving the kernel data buffers to say, here's a pool of data buffers that you can use. And then we later submit async receive message operations with no data buffer in them. Instead, they have a flag that says, take one from the pool. And so now we can have 1,000 connections and maybe 64 buffers. And the kernel will just, as connections receive data, will match them up with a data buffer, copy the data into the data buffer, and then complete the async receive. And then when we're done with it, that data buffer, we can repost it back to the kernel to be used again. So this fixes the memory problem. So we have to, in order to be able to use this from SPDK, and especially in the upper layers, we're going to need an asynchronous socket receive in SPDK. So we're going to have to figure out how to model that. I think right now we're leaning toward having something like this provide buffers mechanism, which is very similar to the what IOU-ring has done. And I think this eliminates the double buffer costs of this, at least in a lot of cases, of this pipeline thing that Seth had outlined before, where we're receiving 8K, because we would be receiving 8K now instead of into an internal buffer and then copying to the upper layers in the NVMe-over-Fabrics target, for example. It would be the NVMe-over-Fabrics target's 8K buffer that it directly receives into. So I think this is a big win all around, and we're going to be exploring this coming up. All right, and then the last slide, there's this concept in IOU-ring today that already exists with a new syscall called IOU-ring register. And this allows you to, what they refer to as register data buffers. And what registering a data buffer means is it means they pinned it and they took a ref count in the kernel. And so the API is extremely unwieldy. But since SPDK's memory is all laid out nicely in huge pages and such, it actually works for us. We can make this function. And then you can do things, there's 2 opcodes you can use with registered buffers called read fixed and write fixed. And so you can submit these asynchronous operations, and they work like a read and a write syscall, except they're on a fixed buffer. And so when they execute, they don't need to copy into a kernel buffer temporarily or from a kernel buffer temporarily into user space. They can just use your user space buffer. And they don't need to incur any extra overhead for page pinning because the memory is already pinned. And so we think there's an opportunity here to use this as possibly a better version of message zero copy in the future. It doesn't really work today. And that's because message zero copy was a trade-off between pinning memory dynamically and copying the data. But if in this mechanism, the buffer is already pinned. And so if we could do like a write fixed on an already pinned buffer into a socket, that could potentially be zero copy with no page pinning overhead. And if you have things like TCP segmentation offload set up in your driver stack, it's effectively a 100% hardware offloaded transmit path, over a socket for TCP. But today, this doesn't really work. The fixed opcodes aren't vectored, so you need to submit a bunch of them. And so that means you need to use IO SQE, IO link. And the abort on partial sends logic with IOSQE, IO-link isn't really explored yet. We're not totally certain that is functional or working. There's also complications with letting us know when the kernel is done with our buffer versus when the data is entirely queued. Today the message zero copy thing, the send completes once the kernel has officially queued it and has guaranteed it has all resources to process it, but not once it's actually done with our data buffer. We do a receive message to check when it's done with our data buffer, but there's only one call here. So I think this is going to take some work on the kernel side, and we'd like to continue to push on this. But there is certainly an opportunity here to do a fully hardware offloaded zero copy, at least send path through TCP that we think would be really awesome. Okay, so looks like I'm good on time and we're all set. So we'll switch over to the Q&A.
Thank you, Ben and Seth. We have about 4 minutes for questions. So if you have any, please use the Q&A panel to type those. If we don't have enough time, we'll follow up offline and try to answer them during or after the event. One question we got, Ben and Seth, is message zero copy. Is it supported in NVMe-over-TCP initiator or only in target site?
Sorry.
Oh, go ahead, Seth. Do you actually know? I know it's in the target site because that's what I worked on. Have we turned it on in the initiator?
Yeah, it looks like we set that directly in the socket module for POSIX, so it's going to be on both of them.
Yeah. So the actual implementation for that is underneath. It's in a socket abstraction layer. So the actual initiator or target don't actually know if we're doing it or not. So it should just work for both. Both sides use the same abstraction layer.
Thank you. One more question. Does the write fixed require a buffer be aligned to size of network MTU?
Right now, no, because the way it's plumbed through the Linux kernel stack is the NIC drivers recopy that data anyway. They don't understand this idea of write fixed. I think they should, and we should think about how we model that. But today they don't actually leverage the fact that the data buffer the user is giving you is actually already pinned and ready to go for DMA, and they just recopy it. So it doesn't work. I mean, it functions, but it's not fast.
All right. Few more questions. Any performance data on Urin, like IOPS per core?
I would highly recommend you go search for the SNIA STC talk given by John Kariuki and Vishal Verma at last year's STC, which contains a ton of data about exactly how fast IOUring is and comparisons to libIO and PReadV and PWriteV, et cetera, and SPDK. So I don't have any in my slides that I can show you right now, but it is certainly available.
Thank you, Ben. I guess we'll answer one more question verbally, and we'll defer the rest to be answered via the Q&A panel. For SQ poll, presumably you want to share that kernel thread with multiple rings. Is that possible? Is that safe?
Oh man, Felipe asking the hard ones. So I'm not actually entirely sure what is possible with SQ poll. I believe it's a setting when you create the ring. So, but I've seen lots of discussion about that exact question on the mailing list. I think it's sort of up to the kernel on how many threads it spins up behind the scenes. I don't think you're really in control. There does seem to be a knob where you can try to set the affinity of the kernel thread when you create it in SQ poll, and I think you can use that to hint to the kernel that things are related. But I would have to go dig into really the kernel code. I doubt that's even documented at this point.
All right. Thank you, Ben and Seth. Great presentation. We'll answer remaining questions via the Q&A panel.